Okay, so we're starting with the shortcut for finding the derivative, which, for those of you who know, you'll know how to do a lot of these, but it's a shortcut that doesn't work all the time, obviously, but it's going to work for the types of functions we look at today, and then as we follow up and get some more complicated functions where the f of x plus h process wouldn't have worked or would have been way too crazy, this is just going to allow us to find the derivative of a lot more types of functions. So the three rules essentially are here. This is the derivative of a constant, always equals 0. So a constant is just a number. So a function equaling 7 is just always going to have a derivative of 0. That should make sense, because if a function f of x equals 7, that's just a horizontal line. And isn't the slope of a horizontal line always going to be 0? So the derivative of any constant number type of function is just 0. This rule, kind of in notation, makes it look more complicated, but this is the power rule. So if you're looking for the derivative of a function, essentially all we do is we take this exponent out in front, so it would be 3x, and then we drop that exponent by 1, so it would be 3x squared. And now if we look back at the rule, you can see that the n comes out in front, and then n times x to the new exponent is always going to be 1 less than it was originally. And that's really the big shortcut that a lot of people have known for a while now, just by talking to kids in AP Calc or other teachers. But this one's very similar. It's just if there's a constant out in front, you keep the constant out in front, and you take the derivative of the function. So for this one, we would keep the 8 out in front and then just take the derivative of x squared by the power rule. So bring the 2 out in front, so times the 2 comes out in front, x to the, and if you drop the 2 down a degree, it would go down to 1, which you don't really even need. So 8 times 2x, which would be just 16x. And lots of times people just think, okay, if I bring the 2 out in front, 2 times 8 is 16, x to the first power, so it's just 16x. And this is where we kind of realize that, okay, the derivative is always 1 degree less than the original function, which was a point that was made when we were looking at the graphs of different functions. So those are the most straightforward versions of the power rule. There's a couple different applications just to think about. So this one has the variable in the denominator, so you would probably want to rewrite this first as x to the negative third. And even though it's a negative exponent, that rule is still going to work. I'm going to bring the negative 3 out in front. It gets multiplied by 5 halves, so that'll be negative 15 halves. X to the, and if I drop that by 1, negative 3 becomes negative 4. And then we can clean this up. So the negative 15 is on top, over 2, and then x to the positive 4th on the denominator. In this example B, which looks virtually identical, the obvious main difference is that this 2x in the denominator is in parentheses. So this would be a little bit different. The first thing I'd probably want to do is change this to 8x cubed, get rid of those parentheses, and then follow a similar method that we did in the first, in the type A, where we bring that denominator up to the numerator but with a negative exponent, bring this negative 3 out in front, so negative 3 times 5/8 is negative 15/8, and drop that exponent by a degree of 1, so it's down to the negative 4th power. Cleaned up, that's just going to be negative 15 over 8x to the positive 4th. So a big difference is to, with that cubed being on the entire 2x versus just on the x. In A, where it's in the denominator and it starts as a negative exponent, you just would bring it out of the denominator just as a positive exponent and follow your power rule. So your 2 comes out in front. 7/3 times 2 is 14/3, and then it'll be x to the first power, which we can just leave as 14/3 x. And then similarly here, we would first rewrite this, bringing the 3x to the positive second out of the denominator. And if you multiply that, you get 7 times 9x squared. That'll get rid of your parentheses, which is 63x squared. So the derivative is f prime of x is 106x. That's from taking the 2 out in front. Just kidding, it's 126. X to the first power. And you know what, looking back now, all of my notations are not exactly accurate. I shouldn't be putting an equal sign here. Well, that does equal. I just rewrote it at first. But here, when I go to the derivative, now I should be doing f prime of x equals. And here I rewrote it so that does equal that, but then I should be saying that f prime of x equals the derivative. Okay, so on the next one, which starts as y equals 3 over x to the 7th, again, we don't want that in the denominator, so I would first rewrite it as 3x to the negative 7th, and then I can find y prime, the derivative of the y function, just by following that power rule. So bring your negative 7 out in front, times the 3 that's there is negative 21, x to the, in the new power, when you drop the negative 7 by a degree of 1 becomes negative 8, and then just clean that up so you don't have negative exponents. The next exercise is written in radical form, so we don't have an exponent on it, but we can easily rewrite that with an exponent. So rather than the 4th root, rewrite it as x to the 1/4 power. So now your derivative on this one, when you bring that 1/4 out in front, that's not bad. But when you take a 4th and you decrease it by 1/4, when you subtract 1 from it, is obviously a common denominator situation. So if we subtract 4/4, we end up getting negative 3/4, which is a little bit more tricky than what we've seen so far, and then we can just clean up the negative exponent from there by bringing that x to the 3/4 into the denominator. And then the next example is a polynomial, which we can find the derivative just by finding the derivative of each piece of the polynomial. So when I jump right into this, I don't need to rewrite anything. Y prime, you're going to take the derivative of each monomial. So the derivative of 4x. Now this is actually new, although simple. That technically has an exponent of 1. So if you bring the 1 out in front times the 4 that's already there, it's still 4. And then x to the first power, when you take a degree away from that, would be x to the 0 power, which is just 1. So you don't have any more x's left on there. So the derivative of 4x is just 4. And the derivative of 3x cubed, when you bring that 3 out in front, will give you minus 9x squared. So the derivative of each piece of a polynomial taken separately will give you the derivative of the entire polynomial. And again, you see that was a cubic polynomial, and the derivative is a quadratic. Just actually one more thing on this. Anytime you have a linear, something like that, I'll add another example. If I want the derivative of this, y prime equals, the derivative of this is just 5, because your x to the first power is going to go down to x to the 0 power, so you lose your x essentially is all that looks like. And then the derivative of 7 is 0, so plus 0, you would just say y prime is 5, which should make sense for linears, because you see the slope of 5, and obviously the derivative is always 5. Whereas in higher degree polynomials, the derivative and the slope of the function depends on the location. That's why there's still an x involved. Your derivative of this function, the slope of this function, since it's always changing, is dependent on what x value you're looking for. So you'll see an x still in the equation for the derivative. Versus a linear, your slope on that function is the same regardless of where you are. So your derivative formula, it doesn't even really seem to be a formula, because it doesn't include an x, because truthfully the x location does not matter. It's always going to have a slope of 5. So just an add-on about linears there. And then just some applications with it. So find the slope of the function at the given point. So we're essentially going to evaluate this derivative of this function at 4. So first let's find f prime of t by taking the derivative of 2, which is just 0. And the derivative of negative 4 over t. Now that I would want to rewrite. So minus 4t to the negative first. So again, the derivative of 2 is 0. The derivative of the second piece of our polynomial, take that negative 1 power, bring it out in front, times the negative 4 that's already there, will be positive 4t t to the negative second, which is cleaned up as 4 over t squared. So if I want to find the derivative at that point where the t, or x coordinate, is 4, I'm just doing f prime of 4, which is 4 over 4 squared. 4 over 16, 1/4. So the slope at 4, 1 is 1/4. On this next one, we need to multiply things out first here. So this x minus 4 squared needs to be multiplied out. Minus 8x plus 16 and distributed. So I'm just rewriting this as a traditional polynomial. And then I can derive f prime of x. On our first term, bring the 2 out in front. That'll give you 4x to the first power. On our negative 16x, that's technically a 1. You're bringing that out front. It'll be just minus 16. X to the 0 power, you don't need to write. And then the derivative of 32, which is a constant, is just 0. So I wouldn't bother writing the plus 0. Just 4x minus 16. Now I'm going to evaluate that at 2. So f prime of 2 equals 4 times 2 minus 16 is negative 8. So the slope at 2 is negative 8. And then lastly with these, again, finding the derivative here. This is not a classic polynomial, so I can't take the derivative of each piece and expect that to give me the answer. So I have to rewrite it as a traditional polynomial. 2x to the 4th minus 3x cubed. And that's still the original equation, just a different version of it. And now for y prime. Now for the derivative. So the derivative of 2x to the 4th is 8x cubed. Again, that's the power rule, so bring that 4 out in front times the 2 is 8, and then x to the 3rd power, minus, and then on this term, bring my 3 out in front times the 3 that's already there, 9x squared. So that's your derivative. It's just making the point that you've got to clean this up into a traditional polynomial first. And then same thing with this one. We want to do the division on each piece, so that'll be a 4x squared plus a 2 plus a 5 over x, which we may want to rewrite that as well. 4x squared plus a 2 plus a 5x to the negative 1st power. So that's all h of x. H prime of x is going to come from the power rule on each piece of the polynomial. So that'll be 8x. The derivative of 2 is 0, so kind of nothing there. And then this one I bring my negative out in front, so turn it to a negative 5, x to the negative 2nd power, and then we'll just clean up that negative 2nd power, so 5 over x squared. And there's your derivative. So your homework is right here at the bottom out of the textbook, and if you have any questions on any of that, feel free to send me a memo, or you can just save a couple questions for tomorrow. But hopefully that was nice and easy, and a breath of fresh air as to how to find the derivative without being all into the limit of the f of x plus h method.